Today we will be seeing the problems, 4 problems. Okay, so we will go with the first question. So here, first, what you normally do is that you normally read the question what they're asking to calculate. Okay, so here they're asking to calculate the brake power of the engine, indicator power, mechanical efficiency, indicator thermal efficiency, and they're asking to draw the heat balance sheet. Okay, so you know the formula for brake power, which is 2 pi nt by 67, indicator power, which is nothing but Pm La and K by 60,000. So we have seen these formulas. Okay, and mechanical efficiency is nothing but the ratio between the power of the brake power to the indicator power. You get the mechanical efficiency, and the indicator thermal efficiency is nothing but the efficiency of the engine considering the in-cylinder of the system. Okay, so here they're asking to calculate the efficiency, and then they're also asking to calculate the heat balance sheet, and they're asking to calculate on minute basis. Okay, the heat balance can be on the second or hour or in minute. So and they're asking to calculate in minute basis and also the percentage. Okay, the heat balance is nothing but it is like a similar what you do a profit loss in an organization. So here heat loss is basically 100% heat balance. You need to balance how much is the heat loss to the system, the exhaust gas, how much is the heat loss to the coolant. Okay, and then what are the unaccounted loss. All these losses you need to capture, and you need to ensure that whatever the heat supplied and the heat rejected, the difference between the heat supplied and heat rejected, and over and above that, you need to ensure that you are going to have 100% heat balance for your problems. Okay, good. So here, this is the question they are asking to determine, and the question what are all the given data. Okay, so here they given that this is a two-stroke engine, and they given that this is a diesel engine. When it was motor, when with the meter reading, this is the power, which means no, the power they given as 1.5 kilowatt. Okay, then the test on the engine was carried out for 1 hour. This is the 1 hour reading, and the following observations were recorded. So they given the brake torque. Okay, the torque is nothing but 120 Newton meter. Speed they given as 600 rpm, and whatever the diesel fuel. Okay, the mass of the fuel is 2.5 kilogram. Okay, when you want to convert to kilogram per hour, which is nothing but mass flow rate of fuel, then you have to divide it by 60. And they also given the calorific value of fuel, which is 40.3 megajoules per kg. And then because for the formula you have the calorific value. Okay, and they also given the cooling water used, because we need to have the coolant to calculate the heat balance sheet. The cooling water used here is also given the mass of the water being used is 818 kg, and the rise in temperature of the coolant water, which means the delta T, the temperature difference is 10 degree, and exhaust gas temperature is 345 degree, and the room temperature is 25 degree. In last class we have seen the exhaust gas temperature difference is between exhaust gas temperature minus room temperature will give you the delta T for the exhaust gas. And they given the air fuel ratio is 32 is to 1. This is the air fuel ratio they given. So now we will see how we need to calculate this problem. Okay, so in your note or in paper, what you do is that you write down all the given data. Now we will solve the problems. Okay, so you please note down the power. I will give you some time. Power is 1.5 kilowatt, and the brake torque is 120 Newton meter, and speed is 600 rpm. Please write down in your note or whatever you have. And the fuel being used is having 2.5 kg. Just give me a minute. Okay, it's 2.5 kg, and you write down that calorific value of the fuel is 40.3, and the cooling water is also this is the cooling water weight. Rise in temperature is 10 degree, and exhaust gas temperature is 345 degree, and the room temperature is 25 degree. And given the air fuel ratio is 32 is to 1. So you need to calculate. These are all the requirements: brake power, indicator power, mechanical efficiency, indicator thermal efficiency, and you also need to draw the heat balance sheet on minute basis. So now I will go with the whiteboard. Okay. So now we will go step by step. The first problem. So first we have to calculate the brake power. Can you display this? Can you please display the display problem slide? What is this? You're not able to see the see my previous slide. Okay, no problem. That so it's okay. That doesn't matter. No need of seeing the problem now. I see. I will write down here. Okay. So brake power is nothing but 2 pi n t by 60,000. Okay. This is the formula that normally we have seen it. Okay. So 2 pi is nothing but 3.14. Okay. Into the pi value is 3.14. What is a n? N is nothing but the speed. Okay. Just give me a minute. The speed. What is in the problem? They given the speed value as 600 or good 600 you have to put into the torque. So they given the torque value as 120 Newton meter. It's brake torque. Okay. Into 120 divided by 60,000 will give you the brake power of the engine. Okay. So this brake power unit is what? Unit is very much important. Kilowatt. Okay. The power is it can be either in kilowatt or in horsepower, but better we will put it in a kilowatt. Okay. The unit you have to okay. So now when you find how much you are going to get. Okay. So you use a calculator. So when you use the calculator, how much you are going to get. So maybe I will also use the calculator along with you. Whether my screen is visible? Whether my screen is visible? Oh, okay. See, it is 2 into 3.14 into 600 into 120. Okay, so it will be like 4 by 2 160 divided by 60,000. So when you divide that 45 divided by 60,000, you get 7.5. So it is not 7.2. When you divide these two, you are getting as 1.536. Yes, 1.5366. is the value, and they rounded to 7.54. Okay, 7.536 or some. You can have it 7.54 also or 7.56, whatever it is. And the unit is very much important. You have to put kilowatt. Okay. Sorry, rounded as 3 point. Okay, no, it's not rounded. Okay. Okay, good. So this is the. So now we are very clear about the brake power. So we have found that brake power. Okay. Now again we are going for. Okay. So we have found the brake power as. How need to erase this one? Okay, one second. Erasing option is not here. One second. Create a next slide. One second. Create the next slide. Stop whiteboard is there. Okay, I'm just allowing the participants to speak. Can you tell where the next slide will be created? Next slide. Okay, you're able to find somewhere. Change topic. One second. Eraser. Clear. Okay. Can I clear it? Can I? The division of 1000 is because the unit of power. Yes. Yeah. Correct. Okay, so now what we have done is we have calculated the brake power, which is nothing but 7.554 kilowatt, rounded to 7.836. And in the problem, what they given is they given the indicated power. Okay, what is in the problem? What is indicated power? It's nothing but a two-stroke engine was motored when the meter reading was 1.5 kilowatt. Okay, so 1.5 kilowatt, thing but the indicated power. Now, the first question what they ask is the okay. Okay. It's not indicated power they given. Take a friction power. Okay, because you see, I told you the friction power has been measured when you are motoring, when the engine is motored. Okay, so in the problem they given, a two-stroke diesel engine was motored when the meter reading was 1.5 kilowatt, which means 1.5 kilowatt is nothing but the friction power. Now, when they ask to calculate you the indicator power, first we calculate the brake power, next they ask you to calculate the indicator power. The indicator power is nothing but brake power plus friction power. Okay, so you need to add 1.54 along with 1.5, so you will get the indicator power. Okay, and so how much is that value? So when you add 7.154 plus 1.5, you get 9.04 kilowatt. Okay, so unit is very much important. Okay, and then next is the indicated that they ask me to calculate the indicated thermal efficiency. Where indicated thermal, they also see the third question is they asking to calculate the mechanical efficiency. The mechanical efficiency I told you, it is the ratio between the brake power to that of the indicator power. So it is the brake power here is 7.54 divided by what is indicator power? Indicator power is nothing but the 9.04. So when into 100, okay, it is always into 100. Okay, 7.54 divided by 9.04 into 100, what you get is the efficiency. How much is the efficiency? So you do the calculation. 7.54 divided by 9.04 into 100. So you will get 83.4. Good. Okay. So this is the value. It is 3.4 percentage is the mechanical efficiency. Okay. So from this you can understand you can increase the mechanical efficiency of any engine when you are increasing the brake power. Okay. And when you increase the brake power, at the same time, you should ensure that you are going to have the friction power lesser. So when you reduce the friction power and when you increase the brake power, your mechanical efficiency can be increased. Okay. So these are some of the conclusions you can get from these things. Next, they are asking to calculate the indicator thermal efficiency also. Okay. So what is the formula for indicator thermal efficiency? Just a minute. Okay. So indicator thermal efficiency is nothing but it is always indicator to indicator power. So indicator power divided by the heat supplied is nothing but mass flow rate into the calorific value of the fuel. So in the problem what they given is so they given the indicator power. So we have calculated indicator power which is nothing but 9.04 divided by they also given the calorific value of the fuel which is nothing but 40.3 is megajoules they given and again what is the mass flow rate of the fuel m dot f. Okay. They given this 2.5 and what is the so indicator power is 9.04 and divided by 2.5 into 40.3 into is always 100%. Okay. And you see here okay, so how much is the efficiency you are going to get? That is very much important. Okay, yes, 2.5. It is mentioned in mass flow rate of is 2.5 kg per hour. Okay, you are right. So we need to divide it by 60. Yes, yeah. The duration is for 1 hour exactly. You are right. Good. Yeah. Again, you also need to convert this megajoules. See, they also given megajoules. The unit what they given is megajoules. Okay. Normally, you need to convert the megajoules into kilojoules. Yeah, exactly. You need to consider the kilojoules to be considered. Uh, yeah, 40.3. So when you're converting that, you get 403. Yeah. So what you have to do is you do the quick answer now. So 9.04 will be in the top into 100 into 60 will be on the top. Okay. Divided by 2.5 into 40300. Okay, 40300. So how much is the percentage now you get? So I'm also doing the calculation along with you. Okay, this answer I have not mentioned in the answer sheet, but I am using the calculator. 9.04 into 60 into 100 into 60. Why I am putting 100 is nothing but in the form of, you need to have 100% in terms of 100. Okay, so I am putting it 100. So in the denominator we have 54240 divided by 2.5. Okay, so 54240 divided by 2.5 divided by 40300 and again into 100. Okay, so it is again, see, when you're converting that megajoules into kilojoules, that it should be again the percentage should be very much careful, and you're getting a 53.8 efficiency. Okay, yeah, you are right. So ratio should be 50.538 you get. So when you put this, it is 53.8. But this is how you have to calculate the indicated thermal efficiency. Okay. And again, what is the break thermal efficiency? Is this whether the break thermal efficiency is given the problem? Okay. So when they ask you to calculate the break thermal efficiency, what you have to put is you have to put the break power here, the numerator. Okay. Instead of indicator power, you have to put the break power. And the break power we have calculated as 7.54. Okay, so accordingly you get a different answer. Normally the indicator thermal efficiency is higher because the indicator power is going to be higher. Okay, higher the value we get higher efficiency. So heat balance for the engine is nothing but the energy supplied and energy distributed. Okay, the energy supplied. Okay, the energy supplied is ES. I'm putting that the energy supplied as ES. Okay, energy supplied is nothing but, we know the mass flow rate of the fuel, which is nothing but 2.5 divided by 60 because into the calorific value of fuel. Okay, they given as 40.3 megajoules. So when you're converting that into kilojoules, we get 40300. Okay, so when you multiply 2.5 into 4030 divided by 60, you get the energy supplied, which is nothing but, see, the unit is very much important. I told the unit is very much important. You see here megajoules. What is the unit they given? That is very much important. You see here the calorific value of the fuel they given as megajoules per kg. So the unit is megajoules per kg. So when you are converting to kilojoules, it becomes kg per kilojoules per kg. Okay, and this kilogram and this kilogram gets cancelled. Okay, so normally you want to have kilogram means what the kilojoules per minute. Okay, so when you're taking the kilojoules per minute, so you are going to divide this by 60. Okay, so what the unit what you're going to get is 1680 kilojoules per minute. This is nothing but the energy supplied. Okay, and now we will see how what are all the now this energy supplied. What you have to do is, so this is the energy supplied 100%. So this is nothing but 100%. And now we need to what we need to do is we need to do the energy distributed. Okay, so we need to ensure that energy supplied and energy distributed both should be 100%. It means the energy supplied should be also be equal to 1680. Okay, so what are all the things will come in case of uh, energy distributed? Okay, so we'll see that one now. So energy distributed is nothing but we have okay, I think this will be still good. Okay, so we need to calculate the heat loss. Now we are going to see the energy distributor. So energy distributor is nothing but what is the heat in the break power. Okay, so the break power what we have found is 7.54. That is the 7.54 is the kilowatt. Okay, and that is, and now you need to calculate 1 kilowatt is nothing but 1 kilojoules per second. 1 kilojoules per 1 second. Okay, so now so this is in second. So now we have calculated in terms of kilojoules per minute. Okay, you remember we have calculated in the form of kilojoules per minute, kilojoules per second. So how many seconds will be a part of a minute? So when you convert that into a minute, so you divide by 60. Okay, so this 60 will go up. This 60 will go up here. So that's why you need to multiply this 7.64 into 60. You get energy supplied, energy distributed in the form of heat. The energy distributed in the form of heat in the break power is nothing but 7.54 into 60. It is nothing but 452.4 kilojoules per minute. Okay, so you know how you got. Okay, so this is how we kilojoules. Yes, we are going to convert kilowatt into kilojoules per second, and again I'm going to convert it into minute. So why I need to have this in kilojoules per minute? Because we have calculated the energy supplied in kilojoules per minute. Suppose if I keep calculating that energy supplied in kilojoules per second, we can have the same thing here also. It is not necessary that you need to have it in kilojoules per minute. Even you can have it in kilojoules per second also. Okay? But the conversion, like see, but what we have put there in the case of energy supply should be the same here also. Okay. Uh, okay, so this is one form. Okay, I told you 100 should be equal to 100 means the energy supply should be equal to that of energy distributed. So we are getting only 452. Okay, remaining have a lot of things. Okay, so we also need to calculate what is the heat loss because of the cooling water and also heat loss because of the exhaust gas, and also the unimportant loss. Okay. So next we will see the heat loss because of the cooling water. So the heat loss because of the cooling water is nothing but mcp delta T. Delta T is nothing but the temperature difference. Okay. So what is the temperature difference they given the problem 10 degree. Okay. So they given this as a 10 degree, and they also given the mass flow rate of the water is 818. Okay, 818, and that is in kilogram. So again, you have to convert that, divide by 60, you need to divide that per minute. Okay, so into this 10 is different. What is the CP value? Okay, so they are not given the CP value. Okay, what is this? So for water, what you have to take is, you have to assume the value uh, as 4.2. Okay, um, you can also take, this is assumption value, so you have to assume that value as 4.2, and this is the value that you have to. Oh, no audio, no audio. Hello, no audio. How come? Yeah, maybe signal issue at your side. Yeah. Okay. So if in case, see this CP value, which is nothing but the specific heat of water is 4.2. Okay, and the specific heat of a cooling of a gas is nothing but 1.05. Okay, so when you have doubt with respect to the unit, let me, okay, just a minute. Uh, oh my God. Okay. Just a minute. Just a minute. 1 point. Okay. The unit of the specific heat of water or a specific heat of gas, it should be in kilojoules per kg Kelvin. I will tell you once, but just ensure that. Just a minute. See here. Uh, See the unit of this 4.2 or 1.05 should be kilojoules by kg into Kelvin. See this kg, kilojoules by kg into Kelvin. This kg and this kg will get cancelled. This Kelvin, the temperature, this Kelvin and this temperature Kelvin get cancelled. Okay, what is left is you have only kilojoules. Okay, kilojoules per minute. Okay, so finally we are going to get the overall in kilojoules per minute. So when you multiply 818 by 60 into 4.2, okay, so finally you get the results is nothing but the heat loss because of the cooling water. Okay. So how much you're going to get? That should be in terms of kilojoules per minute. So you are going to get the final value what I get, I guess 572.6. 570, yes. Okay, so you get 572.6, and the unit is very much important. Kilojoules per minute. Okay, even we also calculated the heat in power and heat in the heat energy supplied is also in kilojoules per minute. Even you can do it in seconds also, no problem. The next important thing is the heat in the exhaust gas, which is nothing but again mass flow rate of the gas into the specific heat of the gas into the temperature difference, which is delta T. Delta T is nothing but the room temperature and also the exhaust gas temperature and room temperature. What is the MT, mass flow rate of the gas? Okay, they given as per the problem. I'm just reading the problem, which is how much is the value? Can anyone tell the value of so here they did not give the mass flow rate of the. So any data is missing because I cannot able to find the value. Okay, to be calculated based on air field ratio, it's is to air flow rate. Okay, how that value 30 comes? No, I think some data is missing in the problem. One second. No, they have to give the value. Okay, see, first we'll go with the known fact. Okay, delta T is no, it is nothing but 345 is the inner temperature and means exhaust gas temperature minus 25 is the room temperature. So this we got this value. Okay, CG we need to assume as 1.05. So you need to assume that as 1.05. So we got these two values. Okay, so only the problem is this is the only problem that we have. And again, we need to divide this by 60. Okay, this also we know. Only we need to find out what is the mass flow rate of the gas. Mass flow rate of the gas is we need to find out the mass flow rate of the gas. Whether it is given in the problem, they given the exhaust gas temperature and room temperature, but they are not given the mass flow rate of the gas. Okay, but they given, you have to see this value, air field ratio, where it is nothing but 32 is to 1. Okay, so 32 is to 1, nothing but the air field ratio. But we need to have the mass flow rate of the gas, which is nothing but how you are going to get the gas. Okay, we have seen the combustion. Okay, combustion we have seen. You are going to get the combustion gas when air is going to get mixed with fuel. Okay, and again, see, it means the ratio what you get 32 is 1. So when you add the air along with the fuel percentage, so you get the mass flow rate of the gas, which is nothing but 33%. So 33, not percentage, it's 33. Okay. Hope you agree with this. 33. And again, here it is, they also given the problem as 2.5 mass flow rate of the fuel. So this is, see, See, this is nothing but the air fuel mixture, and also you also need to see the fuel. Okay, the mass flow rate of the fuel, that is also given in the problem as 2.5. Okay, so this 33 into 2.5 will give you the overall heat distributed form of exhaust gas. So when you calculate the overall value, so what you get is, I'm straight away giving you the answer because uh, we also need to see the other problems already. We are delayed by 60 minutes. What you get is, you get 462 kilojoules per minute. Okay, this is how you get the value. So now we have calculated almost all the things. Okay, so next what you have to do is, you have to calculate the unaccounted loss. Which is nothing but the, the unaccounted loss. Okay, that can be because of many factors. So next one is the heat unaccounted loss. Which is nothing but 1680, nothing but the energy supplied minus what is the heat loss in the form of work power, which is nothing but 452.5, 452.4, and we also got heat loss because of the cooling water, which is nothing but 20.8, and the heat loss because of the exhaust gas, where you find in the last calculation it is coming as 462. Okay, so you need to add all this energy distributed. You need to subtract along with the energy supplied. Yeah. So what we get here is the unaccounted loss, which is coming as 197.8. So I told you this should be equal to this. Okay, the energy supplied should be equal to energy distributed. So now you need to find out the percentage. That is the calculation. That is the question here. So percentage is nothing but the heat in the form of break power, heat loss in the break power is nothing but 452.4 divided by 1680 into 100. Into 100 you will get the percentage of the heat, the break power. And similarly, the heat in the cooling water is nothing but 570.8 divided by 1680 into 100. You will get the percentage of heat loss in the cooling water. And the heat in the exhaust gas is nothing but percentage is nothing but 462 divided by 1680 into 100 will give you the heat loss in the exhaust gas. And the last one is the heat loss because of unaccounted loss. So what the value out of this formula what you got? So what you have to do is that value divided by 1680 into 100. That is nothing but the percentage of heat loss and unaccounted loss. So when you add all these four losses, okay, one in the first one is the break power, next one is the cooling water, next one is the exhaust gas, and last one is the unaccounted loss. So when you add all this percentage, that should be equal to 100%. Okay, this is how you need to calculate uh, this problem. Okay, there is a question. Do we also need to consider the friction horsepower while subtracting? So here, where is the friction power? No. Okay. Here, what we do that all this comes under the form of unaccounted loss. Okay. So you don't need to have that in the form of separately. You don't need to have that is unaccounted loss. But normally we have to take that as break power. Okay. Uh, Break power you need to consider because uh, break power is nothing but indicator power minus friction power. Friction is also there as a part of the break power. Okay, what you get the friction indicator power minus friction power will give you the break power. So whatever the break power you get, still it is the heat loss in the break power itself. Because again we are also doing the unknown loss, even if that is not captured. In addition to that, a lot of losses are there. Blow down loss, blow by loss, pumping loss. Okay, we have seen a lot of losses in the first theory class. We have blow by loss, blow down loss, then what is that? Heat loss, time loss, okay, pumping loss. So all these losses are coming under unaccounted loss. So accordingly it gets adjusted. Okay. So you don't need to separate and you don't need to calculate separately for this friction power because you are calculating the horsepower. Sorry, you are calculating the brake power, which is nothing but the indicator power minus the friction power. Okay. Okay. Good. So this is the first problem we have solved, and we will go with the second problem. Uh, Second problem is also similar. Okay. Second problem is also similar. Uh, yeah, this second problem we have seen it in the last class also, but anyway, uh, I will just give you a overview again. Last class whoever is attended understand, but who are not attended also can understand. Now I will just solve it. Okay, please have the question with you in front of you. If you are not having the question, then okay, I'm directly going with the answer. I think you have a question, whatever I sent to you in WhatsApp. Uh, Four parts to be considered: vapor, coolant loss, and exhaust gun. Yes, you are right. Yeah, you are right. Okay, so now we are going with the second problem. Same you have to consider here also. First, you have to calculate the brake power. Brake power is nothing but 2 pi mp. So here, uh, 2 into pi is 3.14. N is nothing but the speed. Speed they given value in. Okay, otherwise what I will do, this problem I can directly, I think you know how to calculate it now. I will directly go with the sharing screen. Hello. Yeah, sorry, some interruption was there. I just so what we'll do, we'll go with the problem where I'm going to share my screen directly. I'm going to stop it. I'm going to share my screen. Okay, so this problem we have seen in last class, but anyway, I'll just have a overview about this now. So what they given? They given and the following observation were made once see both at a time. Okay. Uh, Okay. Following observation that made during a test. This is also a two-stroke engine. And they given the cylinder dimension bore value they given as 20 centimeter, and the stroke value is also given as 25 centimeter stroke. And you see this the speed they given in RPS, revolution per second, not in minute. Okay. And the formula for kilowatt is nothing but 1 kilowatt is nothing but 1 kilojoules per second. So when you are getting directly in second, you don't need to divide it by 60, not required. Okay. And okay, so now we will see 2 pi, n is nothing but the RPS, they given as 6 value. Okay. And there is even what is the torque. Okay, the torque is nothing but force into perpendicular distance. Okay, torque. See, 2 pi, torque is nothing but force into perpendicular distance. So the given the force is 440. Okay, into perpendicular distance. What is the perpendicular distance? Perpendicular distance here is 0.6, which is nothing but the radius. So our radius is nothing but half of the diameter of the effective brake drum. Okay, the brake drum is always a round shaped one, where the round shape is always having the temperature, the diameter and the radius. But normally we have to take the radius while calculating the brake power. So 1.2 divided by 2 will give you the brake power, which is nothing but 0.6. Okay. So when you multiply all these things, so ensure that here you are not going to divide by 60 because you have a formula in revolution per second. So you're going to get 9948 watts, and again you can also convert that in the form of kilowatt as well. Okay, you can also check it once again the power calculator. Yes, any issue you get, you please let me know. Next, what they asking is, first we have calculated the brake power. Next we need to calculate the indicator power. Where the indicator power, in last problem what they given is they given the indicator power, but here they given the friction power, but here they not given the friction power. And this can be found out using the formula called PMLANK by 60,000 if required. If 60 is required, if required you can do it. Okay, but if it is not there, then we can avoid. PM is nothing but mean effective pressure. So in the problem given the indicator mean effective pressure is 280 kilopascal. Again, this kilopascal needs to be converted to a pascal. 280 into 10 power 3. Area is nothing but pi by 4 t square. What is the diameter? Okay, diameter is nothing but the diameter. So they given in terms of centimeter, you need to divide it to get meter. So 20 by 100 whole square. Okay, and what is the length is again 25 centimeter. So when you're converting that to millimeter, so normally you can have it in terms of millimeter. Okay, that is the unit. It's a unit what we have. So again, we need to divide it by 100. Okay, and into 6. What is the value of k? K is nothing but a constant. Okay. You need to assume that value as 6. Well, is PLN K also will come. Okay. K PMLAN K is nothing but 1. K 1 is the constant value. N is nothing but the speed. And you also have the K factor, but here we are assuming the K factor as 1. So what is the speed in RPS? So here we are not going by 60. We are not going to divide it by 60. We have only we are going to divide it by only 1000. Okay, so to get it in terms of kilowatt. Okay, so already this is given in revolution per second. So we don't need to convert. If it is an RPM, then we need to divide it by 60. Okay, now you have got the integrated power. The same formula how you done the last problem. The mechanical efficiency is nothing but brake power by integrated power. So you know the break power is 9.9 and the indicator power is 30. Okay, and when you do this, you get this percentage. So you need to multiply by 100. Now, what they are asking, they are also asking to calculate uh, direct mean effective pressure of the engine and also the brake power fuel consumption. Okay, so you see here the brake mean effective is nothing but indicator mean effective pressure into mechanical efficiency. You know the mechanical efficiency is 75.4, and it is not in terms of percentage, in terms of percentage is 0.75. And what is the indicated thing? It is 280. When you get this, you get in kilopascal. So even 280 is also in kilopascal. You get the value 280. And the value is also in kilopascal. Okay. Now the very important thing is we are going for the main calculation of heat balance sheet. And before going to the heat balance sheet, we need to calculate what is the fuel consumption in kilogram per kilowatt hour with respect to the brake power. Uh, Here they given the mass flow rate of fuel in the problem as 3.6 kg per hour. Calorific value also given in terms of kilojoules per kg. Last problem they given in megajoules per kg. Now they directly given in kilojoules per kg. This is easy for you now. And they also given the mass cooling water jacket is 460. Rise in temperature of the cooling jacket is 28 degree. It is nothing but delta T. And the air used per kg of fuel is 34 kg. In last problem, they given the air fuel ratio. Now they given the value directly, and the temperature of the air in during the test is 30 degree, and also the exhaust gas temperature they given us 400 degrees Celsius. So you need to multiply 400 you need to subtract 400 minus 30 to get the delta T of the exhaust gas. And they also given the mean specific heat of exhaust gas as one. Last assumption we have 1.05, and here they given us 1. Okay, and similarly the specific heat of water is 4.2. You need to assume that. Okay. So now we have calculated the brake power, indicator power, mechanical efficiency we have calculated. Now we are going to calculate. We also calculated brake pressure. Now we need to calculate the brake power fuel consumption, which is nothing but in terms of mass flow rate of the fuel, which is specific fuel consumption, is nothing but kg per kilowatt hour. And then after calculating that, we need to drop the heat balance sheet using in kilojoules per minute. Okay, even you can have it in kilojoules per second also. And then you also calculate. You need to do the percentage of heat supplied to the engine, and also you need to calculate the brake thermal efficiency. So here they are also asking extra one to calculate the brake thermal efficiency of the engine as well. So the fuel consumption in terms of kilojoules per kilowatt hour, see the fuel consumption what they given is 3.6. The fuel consumption is 3.6 divided by, so this 9.9 is nothing but the brake power. Okay, the brake fuel consumption of the engine is nothing but mass flow rate of fuel to that of the brake power. We have seen that formula. So you get accordingly you get the fuel consumption in respect to the brake power. Okay, and now what is important is last problem we have seen the energy supplied and the energy distributed. Heat is a form of energy. Work is also a form of energy. So now I am replacing the energy in terms of heat. What is the heat supplied by a form of combustion of the fuel per minute? It's 3.6 divided by 60. Okay, I need to convert that in terms of minute, and you are going to get kilojoules per kg. It's already there. Okay, so you get this is the 2550 kilojoules per minute. What is this? It's nothing but a heat supplied per minute. Last thing we have seen as this is the energy supplied per minute. Now this is a heat supplied per minute. Okay, and heat is a form of energy. work is also a form of energy. Okay, now similarly we have to do in the last previous even I have explained last class also. So now what you have to do is, now you have to find out the heat loss in the form of break power. Okay, and we don't need to find separate indicator, sorry, friction power. And you see here, you listen this very carefully. You know the break power, what you get is 9.9 into, so again, here you're going to convert per minute. So normally you are going to get, when it is in per minute, again what you have to do is, so you have got a value kilojoules per second. Yes, this is the form of kilowatt. Okay, kilowatt. 1 kilowatt is nothing but 1 kilojoules per second. Again, when you want to do it, convert that to minute. So 1 by 1 by 60 will become 16 the numerator. So you get this value. Okay. Just seeing whether you are doing it parallelly. You also do the calculation parallelly, because when I am doing it, it may take some time. So I took more time for the first problem. Since this problem is already been covered last week, being very fast. RPM, RPM or RPS, revolution per minute or second. Okay. So again, so I told you again you have to convert this into a percentage. Percentage is nothing but 596.88 divided by 2550. That will give you the percentage, which is 23.41. Next, we have to calculate the heat loss to the cooling jacket, and the value you are going to get is 914. Again, what you have to do is, you need to 914 divided by 2550. You will get this net value. And okay, so let us see how we are getting this 914.5. I told you this is nothing but again mass flow rate out of water into the CP value of water, and delta T. Delta T is nothing but T2 minus T1, which is nothing but 28 degree. Given this in the formula, the problem, 28 degree. Yes, the 28 degree they given. Okay, so 28 degree into K is nothing but the specific heat. Okay, and here 4.17 is the assumption that even in the last problem also we have taken. And you see, mass flow rate of water they given us 468. Again, you have to divide it by 60. So you are going to get the value in terms of kilojoules per minute. So this value divided by this value into 100, you get terms of heat distributed. Okay, it's nothing but heat expenditure. Okay, and then you have to do the heat loss to the exhaust gas, and you're going to get 777. And when you're dividing 777 divided by 2550 into 100, you get terms of percentage. How you need to calculate this heat loss to the exhaust gas? Again, same formula, mass flow rate of the gas into the value they given, the specific heat value they given is one value. Okay, and Tg minus Tr 400 minus 30 will give you the room temperature. Okay. Now we need to calculate the mass flow rate of the gas. Okay, this is very much challenging now. Challenging in the sense, last problem, it is air plus fuel into the mass flow rate of the fuel. But here you see here what they given. Okay, they given we are going to get 2.1 as the mass of the exhaust gas per minute. How we are going to get 2.1? So here they given the air used per kg of fuel is 34 kg. That is a given statement. Okay, and here, so 1 kg of fuel compares with 34 kg of air produces how much it produces. So again, you have to add this 1 plus 34 will give you 35. Okay, and okay, 35 again. You need to divide this by 60 into what is the mass flow rate of the fuel. Okay, they given the mass flow rate of the fuel as 3.6. The last thing they given us air fuel. So we are adding that, and here similarly you have to add here 1 plus 34, so will give you 35. Okay, what is the 1? 1 is nothing but 1 kilogram of fuel when it is mixing with so and so gram of air. It can do a combined effect. Okay, so this is same thing like how you did in the last problem you have to do it here also. Okay, so now we have to calculate the unaccounted loss. It is nothing but the heat supplied, the energy supplied or heat supplied minus the break cover to the top exhaust gas and also the cooling water. So when you do all these things, you subtract, you get the heat loss to the radiation. And again, you need to balance this. Or heat balance, you have to balance this. How you did in the similar fashion, you have to do it in the last problem. So I will also take the last problem here. So we have done in the similar way. In last problem, you have taken 33 and we have 60. This is the mass flow rate of the gas. So it's almost same. Okay, there's no difference between the first problem and the last problem, second problem. And the unit is very much important. The last problem they given RTM, here they given RPS. They are also asking us to calculate the last important formula called break thermal efficiency. Okay, you know the break thermal efficiency is nothing but the heat equivalent of break power per minute divided by heat supplied per minute. You know the heat supplied is given in minute. It's nothing but 2.50, and break thermal efficiency is always related to the break power of engine. Break power is 9.9. So again, this break power is nothing but a heat equivalent of break power per minute. It is again nothing but what you get is 9.9 into 60. This divided by the heat equivalent of break power per minute divided by the heat supplied. You get the thermal efficiency. You need to multiply it by 100. So it is same. There is no difference between the two problems. Okay. Even in the last problem also we have calculated it. The last problem they asked us to calculate the indicator powers. Okay. Last problem. Okay, this is quite interesting. You see here, we have used the formula indicator power divided by heat supplied is nothing but the formula what we use. Okay, so same heat supplied is nothing but the energy supplied. Okay, so it is very so this have to be done the last. It still it will be easy for you. So indicator power is nothing but what is indicator power? They given 9.04 divided by 16. So we got some 53 points something, right? I'm just not giving taking the calculator. 9.04 is the kilowatt. So when I'm converting that into a minute, you get 542 divided by what is the heat supplied? 1680. Oh, okay. So but we are getting a 53 something. Just a minute. Oh yes, I think we made some mistake. We made a mistake actually. So we have again multiplied by the 60. Okay. So normally, okay. So we made a mistake in the last problem. The answer should be like you see you correct this. Please correct it. Okay. We multiplied it by 60. So but you see here. Minute. So it is you know what you have to get to is it is like directly you can do it because already you are going to get the value in terms of minute. It is also minute. You see here. So when you're doing it in minute, what you get is Okay, 2.5 into 40300, okay, divided by 60. Okay, see here we already done it by 60. Okay, okay, I already again I multiplied. So the answer is I made a mistake. So the correct value should be the indicated power, which is nothing but 9.04. And 0.04 divided by 1680 into 60. Again, you have to get the 60 here. Sorry, I'm just confusing. You see here, let us leave about. First, we will see the energy supply. So you would have understood this formula, right? So now the indicator power, what we get is 9.04. This you need to convert in terms of minutes. Okay, so what you have to do is in last time we have forgot this value. So 9.04 into 60 divided by 1680. Okay, this is nothing but the indicated thermal efficiency. We have forgot to divide it by 100. Sorry, divide by 60. So this is the indicated power efficiency. You just correct it. So this should be the value. And similarly, when you're asking to calculate the breath power, you need to do the breath thermal efficiency in terms of like this. Okay. So in last problem, it is indicator power thermal efficiency. This problem it is breath thermal efficiency. Hope these two problems understood from your side. Okay. So similar problems, if it comes, you have to answer it. Okay. Now we go to the third problem. Third problem and fourth problems are very easy, but we will do it. Okay. So in the third problem, what they given is they given the engine is a six-cylinder engine, and it's a gasoline operating on a four-stroke cycle. Okay. Here they given the bore as 80 mm, stroke as 100 mm, and they given the clearance volume VC. VC is 70 cc, and speed is also given as 4100 rpm. So you know the brake power. Okay, so I'll just go with the direct thing formula: 2 pi NP by 60,000. 2 pi n is nothing but 4100. Okay, into torque. What is the torque value? Okay, they given the torque developed is 160 Newton meter, and when you're doing this, you get a value in terms of kilowatt. Even the unit is very much important. Okay, so you need to write the 68.66 kilowatt. And next, what they're asking is they're asking to calculate the brake mean effective pressure. The brake mean effective pressure is nothing but brake power into 60,000 divided by because here again you see here Planck brake power again you see it can be the indicator power the brake power accordingly the Planck by 60,000 will come. Okay. Here they ask me to calculate the brake mean effective pressure. It's nothing but the brake power divided by length, area, and then n into k. You see here the brake power we have calculated 68.66 into 60,000. The length, what is the stroke? What is the length? Okay. Length is again 0.1. It means you can convert it. Okay, whatever the way you want. Even you can have this as 100 also. Okay, you can have that in terms of a millimeter. Okay, accordingly you have to do it. And here they done a conversion. So pi by 4 d square d is nothing but 880 mm, and you are converting in terms of they're dividing it with respect to the conversion, and they're making us 0.08 the whole square into 4100 is nothing but the uh, speed they given. Okay, and you see here, we are going to divide it by 2. N is nothing but capital N by 2 if it is a 4-stroke engine. Okay, if it is a single stroke, in that, sorry, if it is a 2-stroke, in the first 2 problems it's a 2-stroke, that's why we have kept the same direct M value. Okay, but here we need to divide it by 2. Okay, it is a 6 in the engine. Okay, so why 6 is coming here? Again, it is a 6 in the engine. Okay, so number of cylinders. Okay, and divided by 2 is what the number of stroke. Can be either 1 or 2. If it is a 2-stroke, you need to divide, and if it is 4-stroke, you have to divide by 2. And the value what you're going to take is Pascal into Pascal. What is the unit? Okay, and see, 1 bar is nothing but 1 by 10 power 5 Pascal basically. So when we're converting that in terms of bar, you get 6.66 bar. That is nothing but the unit. Okay, the unit of the pressure can be either in kilo, it can be kilopascal or pascal or megapascal. Okay, irrespective of that, you see here, normally 1 bar is nothing but 10 power 5 Pascal. Okay, even how you can define 1 Pascal? Okay, 1 Pascal is equivalent to, okay, but what is nothing but 1? It is equivalent to the bar. Okay, and in terms of Newton meters, see, 1 Pascal is nothing but 1 Newton per meter square. 1 Pascal is nothing but 1 Newton per meter square. Okay, when I say this much Pascal, it is nothing but 6.66 into 10 power 5 Newton per meter square. Newton per meter square. See here, you are going to convert the 100 mm or 80 mm into meter. Why you need to convert that into meter? So this is where the reason. Newton per meter square. One Pascal is nothing but 1 Newton per meter square, which means this is n is nothing but uh, RPM. Okay, and sorry, not RPM, the load, the force by uh, the perpendicular distance, what you call it. So here, square of the distance. So 1 Newton per 1 meter square, which is nothing but 1 Pascal, is nothing but a pressure. Okay, and the Newton is nothing but the load, and the area what you're getting in terms of meter square, which you are going to convert the 80 mm in terms of the area. Okay, that's why you get 0.08 square. Okay, and when you do the conversion, it is nothing but 1 Newton per 1 meter square. You will get it, which is nothing but 1 Pascal. So you need to convert that into a bar. You get this value. You need to calculate. They are asking to calculate drug thermal efficiency. They also given the calorific value of PLS. See, if they are not given the value, you also need to assume, okay, this value, and you have to do it accordingly. So you know the formula of the drug thermal efficiency, which is nothing but drug power divided by the mass flow rate of feed the calorific value, PL, 68.66 is this brake power divided by 19.8 is the mass flow rate of the fuel they given in the problem. They given as a kilogram per hour. So you need to convert that into minute. Okay. Or you need to convert that into a second. When you are converting that into a second into 60 into 60, you will get it. Which means 3,600. 3,600 will go here. And divided by 43,000 they given the calorific of fuel. Okay, so here there is a change actually. There is a change with respect to the question, and the value should be 44,000, not 43. It should be 44 because they go to 44 here. And when you calculate, what happens is there will be a change in the value. $68.66 into 600 into 100 divided by 19.8 is the mass flow rate of fuel, and 44,000 okay, so you get 28.37 percentage. Okay, it is not the 29, it will be 28.37. You correct this accordingly. Okay, yes, the assumption, if you are assuming, you can assume it to 43, but they given the value directly, it is 44. There is a formula for a compression ratio. They are also asking to calculate the compression ratio. See, you have to write. You have to first, when you're solving the problem, you have to write down what are the given data in the problem and what they are asking to calculate. They are asking to calculate the efficiency of a gasoline engine. Okay, the air standard efficiency. You know the air standard efficiency or the thermal efficiency of the Otto cycle gasoline engine is 1 minus 1 by R power gamma, where R is nothing but the compression ratio. Gamma is 0.4. Okay. For calculating R, which is nothing but the compression ratio, you have a formula called the total volume divided by the displacement volume. So the total volume is nothing but stroke volume plus the displacement volume, where the stroke volume is nothing but stroke volume plus clearance volume. Okay, so stroke volume is nothing but pi by 4 d square. Okay, this is nothing but depth of cubic centimeter. Cubic capacity, so you get 502.65, and the clearance volume given as 70 cc. They given the clearance volume in the problem, which is nothing but 70 cc. So when you use the formula 1 minus 1 by R power gamma, you get the value 56 percentage. This is nothing but this 56 percentage, 56.8 percentage is the air standard efficiency using the direct formula. Similarly, when they're asking you to calculate the air standard efficiency of a diesel cycle, you have to use the formula of a diesel efficiency. We have seen the formula. Okay. Now, what the question? The question here is the relative efficiency on a brake power basis, assuming the engine works on a constant volume. They given the gamma as 1.4, and the relative efficiency they are asking to calculate with respect to the brake power. With respect to brake power, you have to take the brake thermal efficiency, nothing but 29.03, and with respect to the air standard, what you take is 56.8. So when you divide these two, you get the relative efficiency, which is nothing but 51.109. Now, when you're going for a brake thermal efficiency of the engine, for final calculation, Okay. It is nothing but brake power. You know the brake power value, mass flow rate of fuel, and also calorific fuel. So here you need to see the brake power, which is nothing but 118.82 into 60, divided by mass flow rate of fuel, which is it's nothing but what is the mass flow rate of fuel? Like when 4.4 divided by 10 into 44,000. So how this 4.4 comes? You get the value here. Okay. So you need to see how that 4.4 comes. Okay. Let us go in the reverse direction. Uh, See, they given the 6-cylinder engine and it is working on a 4-stroke, set to bore, stroke, volume, which they given, and the RPM what they given here is 4,100 RPM they given. Okay, and also they given the, the fuel consumption as 5.5 gram per second, and they also converted that in terms of they themselves calculated in terms of kilogram per hour. Okay, and with respect to this, how that 4.4 comes? Okay. Uh, okay. So I think I also need to correct some values here. So we will stop up to this one. Okay. So I think this is the continuity of some other problems I have clubbed under. Okay. So this is the other problems. Uh, this is the continuation of some other problems. I made a mistake. So the answer ends up to here. This is the answer. Okay. And the answer. Sorry. This is the answer. This is the answer. The answer ends up to here. They're asking to calculate the relative efficiency. Okay. So your answer ends here. So what they asking is they asking to calculate the relative efficiency finally, and we also calculated the remaining things. Okay. So the answer is here because this is the continuation of some other problem which I have taken for some other exercise. Okay. So hope you understand. It's a direct formula. There is no difficulty. So brake power is nothing but 2 pi nt by 6,000, and mean effective pressure is nothing but brake power by the lnk by 60,000, and this 60,000 goes upward. So you get in terms of Pascal, and you need to convert it in terms of Newton per meter square, in terms of bar, and the brake thermal efficiency nothing but brake power where the mass flow rate of the fuel, the calorific fuel. So and again you have to calculate the air center cycle for a gasket is nothing but 1 minus 1 by R power gamma. No, R is nothing but the compression ratio, nothing but Vs plus Vd by Vd. Vd is nothing but the clearance volume. Okay, they given the clearance volume 70, and Vs is nothing but the stroke volume 5 by 4 d square. So with this you get the value directly. So we go to the last problem. Okay, last problem is also very easy. So now let us see this problem in the whiteboard so that we see. Still, we have 20 minutes. So what I will do, I will solve this problem in the whiteboard. But before this, we will see what are the data given. You write down in your note the data given. So it is again given as a gasoline engine, which is specified to be a 4-stroke and 4-cylinder. You note down this. So it's a 4-stroke and a 4-cylinder. The bore is 80 mm, which is nothing but 4. Rope is 100 mm. On it, on test, it develops a torque of this is the torque value they given 75 Newton meter, and the P and the RPM is N, so 3000. And again, they given the clearance volume is 60 cc, and they also given the relative efficiency with respect to the plug thermal efficiency 0.5, and calorific value also they given us 42 megajoules per kg. You need to convert that in terms of kg per kilojoules per kg. And now what they are asking is they are asking to determine fuel consumption kg per hour. They are asking the mass flow rate of the fuel and also the brake mean effective. It is very quite simple. Okay. So these are the things they are asking to calculate. So with respect to exam point of view, so you read this carefully when they are asking to calculate the efficiency of a diesel or a gas. Accordingly, use the formula. Okay, we have seen the converts. We have seen the formula for diesel also. We use the formula accordingly, and accordingly we have to find out the answers. Okay, we read this and again read this. Solve some 2-3 problems similar to this, so that you will also understand. But with the same formula, with the same structure, you can also solve the problems what would you are going to get it in the exam point of view. So it's very quite easy also. Now I go to the whiteboard. Try to read fast now because the time is also running. So first we have to calculate the swept volume. And the swept volume. Swept volume is nothing but pi by 4 t square L. So pi by 4 t square L is nothing but the diameter into the length. So you get a swept volume. Here they given in terms of 80 mm, and you need to convert that in terms of meter. You get to, and again you also need to convert the stroke also, and get the value as 502.4 cubic cc, cubic capacity per cylinder. It's the cubic capacity per cylinder. Okay. And we also seen the compression ratio R, which is nothing but Vs Vc divided by Vc, where Vc is nothing but the clearance volume. Clearance volume given in the problem as 60, and the Vs is nothing but the stroke volume, the swept volume. Okay, swept volume, which we calculate as 502.4. So finally you will get the air standard efficiency. R is nothing but compression ratio you're going to get as 9.373. Okay, and now we have the formula. What is the formula for calculating the air standard cycle? 1 minus 1 by r power gamma minus 1. So you know 1 minus 1 by r is nothing but what we got is 9.3, and gamma is nothing but 1.4 minus minus 0.1 minus 1 you get as 0.4. Okay, so finally you can calculate the efficiency. Now I'm going to share it. Okay, so after finding out the air standard efficiency, right? How much you are getting is 59.14 percentage. In the problem, they given the relative efficiency as 0.5 percentage. They ask me to calculate the breadth thermal efficiency. So when you multiply the relative efficiency to that of the air standard efficiency, you get the breadth thermal efficiency. And what are they asking to calculate? What are the things they asking to calculate? They are asking to calculate fuel consumption and the break mean of 50%. Fuel consumption is nothing but break power to that of means the heat supply to that of the calorific value of the fuel. So then you see here when you're going to the break power, it's nothing but 2 pi n T by 60,000. You're going to get the break power in terms of kilowatt, and we need to find out the heat supply. This also we have seen how to calculate the heat supply. It is nothing but we have seen as mass flow rate of the fuel divided by accordingly 60 or into 60. Accordingly, you need to see if it is kilojoules per minute, you will divide by 60 into the calorific value of fuel. So then you have to apply here. To get the heat supplied, how much you're going to get. So it is not in minute. It is given it in terms of kilojoule per second. Even you can do it like whatever you want to have. Either it is kilojoule per minute or kilojoule per second or kilojoule per hour. Doesn't matter. But you have to write the unit properly. And the fuel consumption. Okay. And normally the fuel consumption is nothing but the mass flow rate of the fuel. It's always mostly in kilojoules, kilogram per hour. Okay. And it is nothing but the heat supplied terms of second they given, and again they are converting that into hour. So that's why you need to multiply that into 3600 divided by the mass flow rate of the fuel. Sorry, divided by the calorific value of the fuel. They given us 42,000. So you get the fuel consumption. And they are also asking to calculate the break mean effective pressure. Also, one of the things they are asking to calculate is nothing but the break power. 23.5 is break power. 60,000 divided by pi by 4 t square L. What you get is the stroke volume. Okay, plant. We also get the BS, the stroke volume or the swept volume. So you get this value, and N is nothing but this for a two stroke. So for four stroke, so you're going to divide that RPM by 2, and the number of cylinders is 4. Okay? It's a four cylinder engine. So when you have the K value is 4, so you're going to get this value. And you see, I told you 1 Newton per meter square is nothing but 1 Pascal, and 1 Pascal nothing but 1 by 10 power 5 bar. So which is nothing but this 10 power 5 get cancelled. So this Newton per meter square is nothing but a Pascal. It converts to a bar. So finally you need to have the value in terms of bar. Okay. So the unit is also very much important. Okay, so with this we are ending this 4 problems. Okay, so practice this. Okay, and also correlate this with some of the other examples. There are a lot of problems